Welcome back. I want to thank again the organizers for this fantastic meeting so far. And I particularly want to thank my co-authors who really, we've come from a wide variety of subfields, as you'll see, and quite a few things we didn't agree on about episodic accretion at the beginning of this, and I think the discussions have been some of the most fascinating discussions I've had in quite a while. So hopefully you'll enjoy the fruits of our arguing. So I just would like to point out that Marco Dart is the lead of this paper, and I'm Joel Green, and I'll be talking about episodic accretion in young stars. So when I talk about episodic accretion, I should, of course, first caveat this. So we probe episodic accretion, or rather luminosity changes, in stars, and we assume in this talk that most of those luminosity changes are intrinsic to the star. That's, of course, frequently not the case. There are smaller flares, lots of other things associated with variable extinction, which can come from disks that might have warps in them, or as they process around, there could be semi-periodic obscurations, clouds, things in the way. That would look like a source of variability. And of course, there are binary effects, and we're not going to discuss those in this talk, but those are something to keep in mind as we go through this. So, why are we interested in episodic outbursts in young stars? So there's a couple of questions I'd like to highlight that have sort of come up over the past 40 years, let's say. Does episodic accretion play an important role in star formation? And for this, I'm going to point out, sort of first describe the two archetypal sources that are sort of the poster children of episodic accretion, F Orionis and EX Lupi and their subgroups. Then I'm going to talk about how the understanding of these objects has changed. And the last review, there was an annual review article by Lee Hartman and Scott Kenyon in 1996, and I believe there's a PP4 talk on the topic, but there was nothing in PP5, and Lee Hartman's book in 98 includes some quite a good review of this as well. But it's essentially been between 15 to 20 years since anyone has really compiled all of the interesting results, and there are entire new sub-branches of this field that have occurred since then, so we'll go through that. Simultaneously, I'd like to think about how how has our understanding changed theoretically? What do we actually understand about these objects that we might not have understood back in the 80s and 90s? And then I'd like to highlight, in addition to sort of the physical modeling, two questions about these objects specifically. Are FUORs and EXORs evidence of episodic accretion? Are they actually evidence of episodic accretion? And secondly, are they, in fact, the same class of objects with different accretion rates? So what are they? Well, let's go back to 1936 here for a minute. In 1936, Fu Orionis, a young stellar object in Orion, erupted. It was traced, it had a 6 magnitude optical outburst in the B, and it's been declining very slowly ever since. So this is over a factor of 100 increase in luminosity. It took place over a course of 3 months, and it has an E-fold decay time of something on the order of 100 years, maybe longer. And it also shows this reflection nebula, which is interesting. If you look at the optical spectrum, and this is a recent optical spectrum, but it had been observed at the time, it looks, to first glance, sort of like a young stellar object plus an infrared excess from an accretion disk, like a T Tauri star. But if you look at the optical peak, it's much wider than a single temperature blackbody, so it can't be. And eventually, it's been shown, it was sort of realized that at first this was thought to be due perhaps to the fact that it was a supergiant or something like that and a misidentified object. But from optical line profiles and other things, they determined that it was a young stellar object and that you can model the entire spectrum with a disk. So all of this is disk. It's just a very, very hot inner disk. In addition, over the next 3 decades or so, a few additional flares, which were very similar in character in many ways to Fu Orionis, occurred, most of them in the Cygnus region. So here's V1057 SIG, V1515 SIG. They also show this kind of reflection nebula, some arc-like structures. There's also V1735 SIG. And these objects show similar magnitude bursts. And together, they became the classical Fu Orionis group, which was FUORs, which were summarized in George Herbig's 1977 paper. Okay, so what's going on? Well, the thought early on and to this day is that there is an episode of accretion ongoing in these stars. So in a normal protostar, let's take a protostar for example here, but you can remove the envelope if you want to consider it a class 2 object. Or a stage 2 object. So you have an envelope, it's got an infall rate of some kind, it deposits its material at the innermost radius, the co-rotation radius, at some rate, let's say 10 to the minus 5, and then that percolates through the disk and accretes onto the star at some other rate. And if that rate does not match that rate, then you must have a buildup somewhere in between the point where you fell in and the point where you hit the star. So there are various theories as to, and then, I should say the infall rate has to be equal to the accretion rate plus the outflow rate, but the outflow rate is usually a factor of 10 smaller. So if you look at Ephurianus, this is a disk model done by Xiaohuan Zhu in 2007 and 2008, and this is his disk model. So what he did is rather than making a disk with an unsteady erratic accretion rate, he took a steady accretion model, added a hot inner disk that extends from 5 times the sun's radius, so which is about 0.5 to 1 AU. This is actually constrained by observations later on. So he has a hot inner region that provides, I don't know why this keeps skipping ahead, that provides the excess. Okay, and this is sort of an alpha disk. And this works pretty well. So how significant are these bursts? So why should we care about bursts? Okay, there's a few objects. FUORs are pretty rare. There's only about 8 bona fide FUORs that have been identified in the past 75 years. I just listed 4 of them. And they're all within 1 to 2 kiloparsecs of the sun. But if you think about if you do a little bit of thought exercise, they actually become quite significant. Within 1 kiloparsec of the sun, if you total up all of the T-Tauri stars in molecular clouds nearby, you come up with the total number of, and I'm just being very rough here, between 10 to the 4 and 10 to the 5 T-Tauri stars. And they have an average accretion rate of something like 10 to the minus 8 solar masses per year, which means that their total accretion, if you add it all up, is something like 10 to the minus 3 solar masses per year. Now, from Xiaohuan's model, FUOR's accretion rate is 2.4 by 10 to the minus 4 solar masses per year. That's a quarter of the total of all of the T-Tauri stars. So even if that's off by a factor of a bit, even if you don't believe that, the fact that there are 8 of them and each of them have accretion rates somewhat comparable to, if slightly less than that, the total amount of accretion occurring in the 8 FUORs is something like 10% of the total accretion occurring in class 2 objects. So they have to be pretty significant. So this is at the moment, they are responsible for 10% of the accretion occurring in low mass stars within 1 kiloparsec. Okay, but now we said there are 8 FUORs in the last 75 years. If you look at the average star formation rate, you get just rough estimates in that region of about 1 star per 50 years. This is a calculation that was originally done in Hartman and Kenyon's paper, and I'm just sort of updating it with the numbers slightly. And so they would agree, and we would agree, that if there are 8 FUORs and 1.5 stars, that tells you that there must be about 5 bursts per currently forming star. So on average, these bursts must occur more than once per star. Now, whether that's distributed evenly or not is not revealed by these numbers. Okay, so that's FUORs. Well, there was another object called EX Lupi, which burst in 1955. And initially, it looks like an FUOR. It has a quick rise time. It's about 5 to 6 magnitudes. But unlike FUOR, it sputters and dies about 200 days later. So this object it was classified as something else, and it was called an EXOR because it was looked upon sort of as a cousin, a weaker cousin to FUORs. So even though it's EX Lupi, it's called an EXOR. Yeah. So then, but what's really interesting is then again in 2008, it had another burst that was almost the same strength and duration. So this is no FUOR has ever returned to its pre-outburst state. So this XOR has done it twice. Okay, so again, why study these sources? So clearly they represent stages. They may represent stages in which most of the mass in YSOs is accreted. At least that's a possibility. We've offered some suggestions as to why that may be the case. So the accretion mechanism then, if you're accreting 10 to the minus 4 solar masses per year, and you're a 0.3 solar mass star, your accretion mechanism may be quite different from that of the typical T-Tauri star. And so there may be new accretion physics to probe with these objects, so they're particularly interesting to study. So they also provide an interesting diagnostic for studying outburst triggering mechanisms, which I'm going to get into just a little bit later. But the infall basically allows the conical wind to be driven from very, very close to the stellar magnetosphere, the surface. And then finally, they offer unveiled or at least low extinction examples of objects with accretion rates typical of early evolution protostars, but with the extinction of a class 2 or something like that young stellar object. And also, they may have very interesting effects on disks. So this is an animation that was made for Peter Abraham's Nature paper. So imagine what happens if a large amount of material suddenly leaves the inner disk edge and lands on the star. This is not going to just change the system luminosity, but it'll cook the entire disk and have very interesting chemical and other effects that have been already referred to in earlier talks. So what is the global statement we can make about all of these objects? Well, all FUORs and XORs do have some common properties. They are all low-mass pre-main sequence stars with infrared excesses. So they all have disks, gas-dominated disks. And they all, of course, were identified by their fact that they show strong optical outbursts. And their variability is primarily accretion-driven, although not, there are other causes. OK, so go back to 1977 again. Imagine that you look at George Herbig's paper, and he looks at all of the at that point, currently known FUORs, or objects in the FUOR and the EXOR class. Right, so the FUORs, they're really quite obviously distinct here. This is FUORI, it's V1057, these are light curves, and this is V1515. So they do have different rise behaviors, but none of them are decaying significantly. And then it's sort of quite apparent that EX loop and these other ones are on a completely different time scale. So there's certainly a short and a fast mode of burst accretion. OK, so one suggestion is that FUORs are perhaps less evolved than XORs. Maybe they're earlier stages. It had already been suggested from submillimeter observations that FUORs were a lot like class 1 protostars, and from ISO as well. And now that we have Spitzer and Herschel, we can do we get a little more data, and you can do some direct comparisons. So, for example, let's start up here, actually. So this is the luminosity of the 01 63 micron line, which was observed with Herschel, and the bolometric system luminosity. And the black and white squares are class 0 and 1 protostars, and the X'd boxes up here are the FUORs. And they certainly continue the trend quite smoothly that you were seeing. And in fact, if you include higher luminosity sources, such as those in the HOPS program, you fill in this spot with protostars as well. So they're not particularly well distinguished from protostars by this measure. And that tells you that whatever is exciting the 01 must propagate quite quickly or predate the outburst, because some of the objects in here burst less than 2 months before the spectrum was taken. So that's one way in which they're similar. The other way in which they differ a little bit from protostars is if you look at their total SED, and we now have Spitzer IRS spectra, Herschel PAX, and Herschel Spire. And this is a typical class 1 protostar from the Taurus cloud called TMC1. And this is an FUOR, actually one of the ones that has more extinction toward it and tends to be considered one of the more embedded. And it is still, although it does have a big excess, it is redder than a typical class 1 protostar. So this is sort of a laundry list of properties by which these categories are defined. I'm not going to go through the whole list, but what I'd like to point out is that in many of these properties, individually, there is significant overlap between the two classes. Not all of them. For example, the burst decay time is the most obvious distinguishing factor between these two classes, but it is not immediately apparent when something goes into burst which of these it is. So keep that in mind. So FUORs themselves are sometimes split into subgroups, the more embedded versus the less embedded, the flared disks options. And both of these models work very well. And the attraction of the envelope in particular is if you're going to have repeated bursts, you need some mass supply to provide the disk with more material to continue the process. And it also is very important for models that I'll be discussing later. So Sasha Kwan's in 2007 made an attempt to sort of distinguish these categories by their Spitzer spectra, their mid-IR spectra. And he found that, so for example, some of them show silicate features in emission, some in absorption, and they have different SED shapes. So, but his proposition is that they're the same objects for the most part, but with a different viewing angle, in this case looking through much more of the infalling envelope, and in this one looking through the carved cavity. So to a much clearer view of the disk directly, and this is certainly a possibility that the inclination effects cannot be neglected. Okay, so great. So now we have sort of a procedure by which to drop these objects into different bins, and we can determine what they are, and this is all great. So then what happens to ruin us is a whole bunch of new outbursts that don't fit into either category at all. So here's one, V1647 Ori. It's McNeil's nebula. It burst first early in Spitzer's lifetime, so there's some great Spitzer images of it. And it has a very, very short duration burst, like an XOR, but it is rather embedded like an FUOR. This one is HBC 722. I'm going to call it by that name so you don't confuse it with the next object. This was a burst in the North America, well, just south of the North American Nebula, so it's referred to as the Gulf of Mexico. But this is 2009, this is 2010. This object was only a half a solar luminosity when it first burst, and now it's about 12 to 20, something like that. So it's one of the wimpiest FUORs out there, but it is an FUOR because of the light curve, which tricked us for about a year. So I'll show you something in a moment. But let me just skip past that. V2492 SIG, quite close by, is an XOR. This one had a slow rise time just like the FUOR, but then almost immediately disappeared. So what do you do with these? So this is really highlighted by this plot from Agnes Kosbal. These are the classical, 3 of the classical FUORs from the review, and they're beautiful light curves with their admittedly different rise times, but all have long decay times. Okay. So after a little while, you can tell which type you're in. Now, this is V1057 SIG, so that's an FUOR. And this is EX loop. It's got the nice short burst. That's an XOR. Everything else here is a mess. So V1647 has slightly longer burst, but is pretty embedded. We called it an XOR. V2492 has been sputtering for quite a while. HBC 722 is particularly interesting because it faked us out. Here we thought it was an FUOR. This is a classic FUOR rise profile. And then it started to fade quite quickly. And so about this point, we declared that it was an XOR. And then it flattened and has been rising ever since and is now brighter than it ever has been. So it's now been 3 years, and it's still going up. So now it's definitely an FUOR. OK. So that didn't particularly help us determine which classes they are. So let's talk about the X-rays. Maybe that has something to say. So this is basically a new field since 1996. These observations just weren't done before that. So do the XORs track the accretion process as well? And can they help you distinguish between the classes? So if they track the accretion process, then they should follow the light curve, which in this case, this is V1647 Ori. The X-ray light curve looks like a beautiful mimicry of the infrared light. So that's great. And then you look at V1118, and it doesn't particularly, although there is a slight correlation, it doesn't particularly well follow the infrared. It rises, but much more slowly. So there is some evidence that the soft X-rays and the XORs arise in accretion shocks. Some of it, probably not all of it. So what about FUORs? Are they different? They are different. They're X-ray bright. So 4 of them have been studied. This was a series of studies by Steve Skinner and Manuel Gudel, and collaborators. This is sort of the Titori extrapolation. So they actually, if you look at this is the X-ray luminosity versus the bolometric luminosity. And note that in the case of the FUOR, this is star plus disk, where over here it's just star. They are X-ray bright, but not particularly for their luminosity. And furthermore, only 2 out of the 4 are actually detected. So, and of these 2, they're both different. V1735 shows hard X-rays. FUORI shows both hard and soft X-rays, with the idea that in V1735, which is one of the most embedded of the FUORs, it's perhaps obscuring the soft X-rays through a large column, whereas the hard X-rays are not as badly depleted. And also, the problem is, though, that FUORI is also suspected to be a binary, and sometimes the X-ray component might be associated with the binary star. So there's a lot of complications there. So V1647 is particularly interesting because it has, once you remove all of the intrinsic luminosity variations, remains this very robust 1-day period that's stable over a period of it's been stable for 5 years. So it's quite robust, and Kenji Hamaguchi modeled it with a pair of spots on the star that are rotating around. And so this suggests that the star and disk geometry, magnetospheric geometry, is highly stable, yet if these spots are accretion-driven, then you might expect some more chaotic effects. The other interesting diagnostic you can get from FUORs is regarding outflow driving. So this is a model from a figure from Ariel Koenigel's paper, and this is work by Marina Romanova and collaborators. And it shows that if you have a large amount of material coming in, it compresses the magnetosphere of the star to quite close to the stellar surface, which means that you can now drive, and then she shows that you can actually drive outflows or wide-angle winds, whatever you want to call it, from a radius very, very close to the stellar photosphere, and yet have them become wide-angle out there. So this is sort of a justification for the geometry of some of the figures I've been showing earlier, and it's certainly an interesting test case for this. And the idea is then this is, of course, twisted up by magnetic energy and then spun out in an outflow. Okay. So I haven't talked much about the infrared observations of EXORs yet. So what I'm just going to point out one thing here. Peter Abraham, so one of the advantages of XORs is that they have very short timescale bursts, and you know which objects to look at fairly quickly because they repeat. So you can get a pre, post, and during outburst spectrum. And this was done with Spitzer IRS, which was around when EX-Loopy was an outburst. So here it is in quiescence. This is the 10-micron silicate feature, which is the optically thin dust hanging up on the surface layer of the disk of EX-Loopy. So in quiescence, it shows relatively pristine feature, maybe some different grain distributions, but no signs of dust processing at all. This is in direct contrast to a large fraction of regular classical T-Tauri stars, which typically show processed dust in their silicate features. But when EX-Loopy goes into outburst, these bumps are real. This is an increase in the crystallinity fraction. There's a couple of different components here from forsterite and I think probably enstatite. This is magnesium-rich dust. So either dust has just been processed or it's been stirred up. One of the two has happened, and it's happened on this timescale of months. So this certainly suggests that either rapid processing or transport are quite likely in disks. So then this kind of brings up the question, what actually sets the conditions in a protoplanetary disk? So in the usual paradigm, the class 1 protostar lifetime is 0. Let's not say how many mega years, given the arguments that have been happening here, during which the envelope thins and eventually disappears, and the accretion rate, which starts at a very high level, slowly dissipates while planets form by different processes. Okay. So is this a stable process, or is it interrupted by bursts of episodic accretion? So, of course, and Lee Hartman has proposed this sort of empirical model in which you start out with a high accretion rate and you do gradually fall, but you're punctuated by these bursts which are attributed to F-Urionis events, and then later on, the slightly lesser bursts are supposed to be XORs. Now, for the first time, we actually have models that might agree with this. So this is from Edward Vorobyov and Shantanu Basu. So here they actually predict the appearance of bursts with duty cycles roughly appropriate to reminiscent of the cartoon model in FUORs, along with smaller scale effects from flickering and other things like that. So this is how much you have these bursts. So within a disk, so this is a model from Xiaohuan Zhu. This is a magneto-rotational plus gravitational instability model. So I'm going to describe this briefly. The idea here is that the gravitational instability, when the disk is massive, heats up the disk. When you approach a high enough temperature to raise the ionization fraction in the inner disk to the point that a magneto-rotational instability can turn on, the accretion rate is quite high and efficient and easy. When there's no MRI, the accretion rate is lower. The thing is, if these two don't always meet up. So there may be a bottleneck region where there's not really a GI to heat up the disk to a sufficient fraction to ionize the material such that the accretion rate can proceed at a high level, thereby creating a pileup here until such time as so much mass is there that it overwhelms this and goes through into the star. So this is one way you might get this. And so this he sort of predicts a transition region in the 1 to 10 AU regime. from this junction. So the advantage of this is this actually predicts the outburst strength and time scale quite well. But the details of the MRI triggering by the GI are really uncertain. So this is here's another. So imagine you still have a GI disk, but the two-ray Q parameter is still around 1, but the disk cooling is now effective. And so this is farther out. And earlier, when the disk is more massive, then the disk can fragment. Okay, and so here's an example of disk fragmentation. So I'll just play this movie. So did it work? Yes. So this is the disks. This is the material spiraling in. There's an envelope out here. It's falling in. So this black is not empty. The idea is that there's an envelope with an accretion rate of 10 to the minus 5 solar masses per year pouring in here. And as clumps form as clumps form from the fragments are then pushed in from the outer disk into the inner disk. And this shows the accretion rate as we would measure by the luminosity bursts resulting from the fragments falling in. So I'll let this play for a minute just so you can see what kind of light curve it generates. So here's your F Orionis burst, and then if you wait a little while, there should be another, yeah. So but in between, it's not quiet. There's little smaller scale bursts. All right. So if you look at sort of the typical light curves produced by these models, of course this model requires the object to be embedded and to have an envelope that's still feeding. So this doesn't apply to every single F Orionis object or the XORs very well. But it does produce light curves that sort of look like the kinds of variability you might see on smaller time scales in any of these objects. So it does scale down. It's just that you need more cells to get the kind of resolution where you could translate this to a time scale where these are equivalent. Now, this works great in the embedded phase, but when you've gotten rid of the envelope, you're kind of stuck with 1 or 2 bursts, and that's it. So that's when you might turn to planet-induced bursts, okay, which have a more regular time scale, or binary companion interactions, which are related. Okay, so the other thing that we can measure and look for is chemical markers, which were discussed in several of the previous talks. I'm just going to point out 2 of them here. For example, the CO gas, so as CO is liberated off the grains in some of these outbursts and ends up pouring into the envelope, the CO gas fraction should increase. So objects that are currently outburst or recently had an outburst should have enhanced CO gas. Likewise, there was a discussion of the irreversible effects on CO2 ice, which was discussed in Amy Stutz's talk yesterday. So both of these effects might indicate that an object that is now not currently bright had previously undergone episodic accretion. Okay, so what can FUORs and XORs contribute to our understanding of young stars? Well, are they regularly occurring events, or are they evidence of episodic accretion? And I think we've now compiled a real laundry list of reasons why these objects probably are evidence of episodic accretion. And they come from both observation and theory. So first of all, as I said at the beginning of the talk, the observed burst timescales and the accretion rates and the lifetime estimates all agree with the idea that a decent fraction of the accretion is occurring in these sources specifically. And that the preponderance of low luminosity sources, fellows, very low luminosity sources, in some sense balances the distribution so that you average out to the typical T-Tauri 10 to the minus 8, but you have both the high and low states represented. They offer a partial solution, or some of the solution, to radial and vertical transport of processed dust. So this is, I think somebody asked a question in an earlier session about how you might have processed dust that have been in the inner solar system that we now find in outer solar system objects, and it's possible that you could produce them by a method like this and then blow them out violently in winds or just gradual transport later over the lifetime of the disk. And that's both radial and vertical. But we know that at least some layer of the disk changes on quite rapid timescales from the variability of the silicate features. By the way, I should point out that FUORs show nothing but pristine silicate features. They have only unprocessed dust, but no one has ever observed an FUR post-outburst because none of them have ever returned to outburst. So we'd need to wait quite a bit longer to see if that is still the case. In fact, I actually have a SOFIA proposal to look at some of these objects, so we'll see if that goes through. Oh, and then of course the theory, as I've said earlier, matches the cycles that we predict from these from the number statistics. And there are the chemical markers. And finally, one thing I haven't discussed, but there's certainly some evidence from outflow morphology, the fact that some jets and outflows look episodic in nature, the idea that if outbursts are not steady, then perhaps the infall that generates the outburst is not steady, and the two are tied together. And finally, are FURs and XORs actually the same thing with different accretion rates? And I think the answer 15 years ago would have been definitely not. But now, it looks like they really do kind of merge, and you have these hybrid objects like V1647 Ori, V2492 Cygni, and HVC 722 that really blur the careful categorization of the two objects. So the primary remaining distinction then that you're left with after all of this is the timescale. So how can we do episodic accretion studies in the future, and what advantages will we have that will enable us to kind of disentangle some of these effects? There's a few obvious ones. For everyone's favorite instrument, ALMA, of course, is fantastic for this because it will really allow us to accurately determine the evolutionary state of the objects by using the continuum and line imaging to derive envelope and disk masses and determine whether a gravitational instability could work, or what state, are these the more embedded objects, are these really just an inclination effect, are these objects really in separate, are these objects really distinguished this way? So ALMA will provide quite a bit of help there. But perhaps just as important are the surveys like the Palomar Transient Factory and LSST eventually, which will provide continuous monitoring of large areas of the sky, much in the same way you might want to look for supernovae. If you can find evidence of a burst early on, you can measure the interesting physics that's going on at the origin point. And so it's sort of been a game to try to catch these things as early as possible using telegrams and things like that. And finally, so that allows us to presumably increase our sample of bursts. And then finally, WISE provided an all-sky snapshot in 2010, and that it's in the infrared. So now, when we compare new images, and even older ones, against the WISE background, we will find objects that have shown infrared bursts and not just optical. This may lead us to find more of the embedded sources relative to the number that we've been finding currently. So in the end, I suggest, or we humbly suggest, that perhaps it is best to start moving away, just gently, from the FUR versus XOR distinction, and just treat them as extreme bursting young stellar objects and evidence for episodic accretion, and then apply all the models that have applied to the regular objects to better understand these accretion burst mechanisms in objects which highlight these unusual cases. And then we can identify the key parameter controlling the bursts, of which there appear to be several, and hopefully constrain some of these parameters. And I think what the important thing to point out is that these objects, which really used to be extreme curiosities, are really not. They're actually fundamental to our understanding of the evolution of young stars, and I think are worthy of greater attention in the next, by PP7. So thank you very much.
Okay, so now time for discussion. Okay, yeah.
Jonathan Tan from University of Florida. I'd like to question this fraction of accretion in YSOs that is in burst mode. As I understand it, you were counting up of order 10 to the 4 to 10 to the 5 YSOs.
Within 1 kiloparsec.
Right, and then giving them 10 to the minus 8 accretion rates. But you know, we think they formed in less than 1 million years, so why didn't you give them 10
Class
to
2
minus...
objects.
Right, but the overall accretion to the stars would have occurred at rates more like 10 to the minus 6 in each star.
Is that the time average total? Would you say 10 to the minus 6? I mean, 1 million years, you have,
maybe
let's
higher.
see. Well, so it's not that the, so here's the answer to your question. So the FURs are not as comparable, although I've just argued that they do have some properties in common with protostars, they are among the more evolved objects. So the properties to compare them to are the more evolved objects and their accretion rates. So the fraction of accretion that I'm referring to is the fraction of accretion that's occurring in the more evolved objects. And they're probably, I mean, the cartoon picture would suggest that these bursts occur in earlier phases, but one of the points I was trying to make is that it's actually very hard to see F Orionis objects in a class 0 protostar, first hydrostatic core kind of situation.
So
Does that?
basically the fraction.
So it's an extrapolation.
The fraction of total accretion in bursts
is not 10%.
Is unknown.
That's right. But, well, that being said, the amount of accretion, amount of material accreted by F Orionis in this one burst is something like 1 to 200th of a solar mass. It's a 0.3 solar mass star. So right there, you get one burst, 3%. So it can't be too low.
Okay, so this side.
Tom McGath, University of Toledo. One of the issues that we have is we like to know which sources that are FUORI objects that are actually in the process of bursting, which people haven't observed the burst, particularly for protostellar objects. Do you have any ideas or hints or clues of how we might actually find such objects?
Before they burst?
Yeah, well, no, the objects where the burst has already happened.
After
they're
they
in the
burst.
process. We can actually count how many objects, say, in a certain cloud are undergoing a burst without actually having observed the burst itself, because the burst is historical.
Do they have spectral properties that would, or do they have SED properties that would indicate that they're in burst?
Or variability.
So the near-infrared is, well, for more evolved objects at least, the CO bandhead emission. You see these double-peak line absorption profiles, which presumably are generated by having a hot midplane and a somewhat cooler but still 7,000 degree disk photosphere in these events. So if you see an object, if you take a near-spec spectrum of it, you might be able to distinguish them. That seems to work for some of the objects. It's not a universal, but it's a good way of identifying them. The other is if the optical peak is far too wide to be generated by the star, and it's an evolved enough object that would be, it's not so extinguished that with protostars it's trickier, because most of the tracers you get are wiped out, because they're not apparently particularly X-ray active for their luminosity, so they're not well distinguished by that method. So the more embedded you get, the harder it is to identify these, which is kind of what I was trying to say to Jonathan as well. So we're still working on that.
Okay, so up there.
Yep. Bertrand Goldman, MPAA. Bertrand Goldman. So you mentioned LSST, but
Yes.
you
Sorry.
don't have to wait for that. I mean, there will be Pulsars 1 with 2 years of data already.
And PanStars 1, yes.
And Yal Deacon and his student Yadav are looking at this right now, so stay tuned.
And YSO VAR as well, I think. There are some Spitzer studies that may also reveal some infrared. So this is definitely, I would say that the number of F Orionis bursts that we're going to see in the next 10 years is just statistically, not because there are more bursts, but because we're going to have a lot better coverage, is going to greatly increase. If you look at the names of all of the objects I've been presenting, they all end with Ori or Sig, just about. And so there's some huge observational biases, as well as, of course, those are the largest clouds. You'll notice I didn't really mention any southern hemisphere objects. As soon as we fill in, as soon as we have better sky coverage, more of these will pop out, and we'll have a much better chance of establishing whether these really are oddities or are part of a larger class.
Okay.
Chris McKee, Berkeley.
Yeah.
I just wanted to ask, if you compare the FUORs and the XORs, what is the relative amount of total mass that would be accreted by these two classes of events?
Well, it's much, much smaller in the XORs because their average accretion rate is at least a factor of 10 less than the FUORs, and their burst duration is a factor of 100 less, so about 1,000th as much.
Right, but then there may be more.
But there are way more of them, yeah.
Yeah, so I want over the lifetime of a star, what would be the relative amount of mass accreted?
I haven't totaled that up.
Well, okay,
If you take EX loop as an example, and it's had 2 bursts in 50 years, and each burst has accreted 10 to the minus 7 to 6 solar masses, and that phase is supposed to last, well, if it lasted for the entire T-Tauri phase of a couple million years, that's actually quite a large amount. It's like half a solar mass, so it can't go too far into the T-Tauri phase. I think it's safe to say that there's some consensus that the EXORs are not the most evolved T-Tauri stars. They're not the most evolved class 2 objects. While they could be classified as class 2, they definitely have full disks. They're not transition disks. They don't have low accretion rates, even in quiescence.
Yeah, Willy Klei, University of Tübingen. I have a question concerning the outburst mechanism. I mean, there used to be these models around by Robbins-Bell and others, the disk instability models. Are they ruled out by the observations?
No, they're not ruled
or are they
out.
still up to date? I mean, because you didn't list them in
I didn't list them because I was bringing in the models that drove repeated bursts. I didn't really. So one of the points is that if you supposedly have multiple bursts per star, and each burst is going to accrete 100th of the solar mass, and that's the typical mass of the disk, then in the earlier phases you really have to have something involving that can be repeated, a burst that doesn't drain the entire disk mass out, and so you're stuck using some kind of reservoir to refill it. But there's nothing that stops disk instability modeling. No, not that I know of anyway. My co-authors could correct me on that.
Okay, so upstairs.
Aurora Cecilia, and, Madrid. Yeah, so I just wanted to make a small comment. You just mentioned that XORs don't have low accretion rates even when they are quiescent, and they also they are not something like transitional disks also. But actually, X-loopy doesn't have a very high accretion rate when it's in quiescence. It's like few times 10 to the minus 10 solar masses per year.
That's
and
true.
Actually, even when it's in outburst, it
10 to minus
increases by
7.
2 orders of magnitude or so, but it's not extreme. It's a few times 10 to the minus 8. And also, we are also wondering whether it has a small hole. Not a huge one like in transition disks, but 0.3 AU or something like that, it could be actually.
That's EX-loopy was maybe not the best example. There aren't very many XORs, so if you only have a sample of 4, it's tough to average the properties over the group. There aren't that many more FURs, but there are a few more. But I take your point. It could be a more evolved object, except for the silicate feature being pristine. That's actually often taken as an evolutionary indicator if they're processed.
Okay, so
Yaroslav Pavlyuchenko, Russian Academy of Science. I would like to ask you an explicit question. So, do you think it is possible to form massive stars by episodic accretion? So, maybe this mechanism can overcome this Eddington limit for the accretion.
I haven't thought much about it. I mean, the timescales are much shorter in massive stars, so I think these mechanisms are maybe not as applicable, but whatever happens I think it would be analogous to what happens in the earlier collapse phases of protostars, or more the sorts of properties that would drive high mass stars. You're waving your hands. Do you have an answer for this, or? No, okay.
okay, yeah, this side.
Sergei Nayakshin, University of Leicester. Since we are moving towards planet formation in this meeting, I thought it's appropriate to make a comment that the processes that you're discussing here, these clumps migrating inward, are actually processes that we think may form giant planets in the outer disk. And if you actually model this in greater detail at smaller scales, inside 10 AU, what you get is that these clumps are actually young planets. And when we get in towards inner AU, you can show that they can be tidally disrupted and stripped, leaving behind hot Jupiters, hot super Earths, and hot Neptunes. So, I and Giuseppe Laudata had a paper on it last year, where we did the calculations, and the light curves actually look great. We reproduced FUORI and XORS type outbursts as well. So I think it's, very, very relevant to planet formation.
Absolutely, yeah. Thank you.
Okay, yeah, this side.
Thank you.
Brinkfried Strecktum, Taubenburg Observatory, over here. You mentioned that many triggering mechanisms, MRI, among those requires high ionization of the inner disk to make it work, right?
More efficiently.
So I presume that those disks, at least the inner parts, look similar to the disks around massive stars, which are well described by the Hollenbach model. If this is the case, you would expect quite some radio continuum emission because of the free radiation. So I'm not aware of many work which has been done in the field, because they should be variable at those wavelengths as well, right?
I mean, at millimeter wavelengths, they look like protostars. The radio.
No, I'm talking about centimeter.
Yeah, I don't remember off the top of my head I mean, there are outflow maps, but I can't remember what. I'm not sure what the radio emission looks like.
Okay, so yeah, upstairs.
Hello, my name is Hendrik Linz from MPIA Heidelberg. I have a comment on episodic accretion on young massive stars. The question was out there. There is some evidence for this based on masers. Yep. So there is more and more data emerging that you have not only flaring masers associated to the massive stars, but also periodic variability in these masers. And I think the mechanism is still not so clear, but one proposal is that you have a binary system, you induce some accretion from the circumbinary material onto one of the components. This increases the infrared luminosity and this pumps the masers. So this might be something to follow up.
Absolutely. I should point out, although I could only cover certain fractions of our chapter, that we at least address some of these things in the chapter as well, and in quite a bit more detail than I presented here. But that's in particularly a good point.
Okay, so last question.
Andrea Banzatti, ETH Zurich. I thank you for the nice review that gives the FURs and XORs the importance they deserve. And I just wanted to add a quick comment that with Peter Abram and Mike Meyer and other people in this room, we had a nice result that I believe it's important because it sort of connects what you said in your review to what was said this morning about volatiles and watering disks. That we found that not only dust grains are processed during XOR outbursts, but also the molecular gas in the inner disk, like water vapor and organics. And if you want more details, I can point you to my poster that will be visible in the 2 sessions now, which is 2S034. This is the phone number.
Great.
Thanks.
I didn't want to be so presumptuous as to claim that the FURs explain the reset that was referred to in the previous talks, but clearly it's connected. So, thank you.
Okay, so please speak again.